Thank you everyone for joining us for this webinar on RAMDO solutions. We're going to give a brief introduction of RAMDO here. We won't dive into a ton of technical details. If you have those questions though, we can answer them at the end or offline. We'll run through a quick introduction, some examples, and give a live demo as well during the course of this. So a little bit of background on the company itself. All the stuff developed in RAMDO originated as research at the University of Iowa under Professor K.K. Choi's group, which some of you may know. It's primarily all funded by DoD through the Army, totaling about $4 million in funding over the years, and produced about 10 PhDs. The company was started up in 2013, the end of 2013, really got going in 2014. And DoD's continued to support us in seeing the commercialization of this through SBIR grants from the Army, through TARDEC, and you can see there we've got just a little over $2 million in funding from them so far for commercialization efforts. So what is RAMDO? RAMDO is a complementary CAE tool for carrying out uncertainty quantification, reliability analysis, and reliability-based design optimization. Basically, RAMDO is a tool for handling and working with uncertainty and variability when you're designing products or carrying out simulations and trying to study something simulation-based. Why is RAMDO needed? Uncertainty and variability is pretty much everywhere: manufacturing processes, material loads, material properties and loadings, and the list goes on and on. The real question is how much is that uncertainty and variability impacting what you're trying to do or produce? So what's RAMDO's key benefits? The advantages of RAMDO highlighted at a very top level is reduced computational time. This reduction in computational time is actually a reduction in minimizing the number of simulation runs required in order to carry out the uncertainty quantification or the reliability assessment. And this is one of the unique features in RAMDO that kind of distinguishes RAMDO apart from other uncertainty tools that exist out there. The other key thing of it is we've developed it in such a way to still maintain very highly accurate results with the minimal simulation runs needed and required. And so the end benefits is you can produce products, designs that are more reliable, improving safety, you can reduce weight, noise, cost, whatever that might be. And also just having the knowledge of how variability affects your design or your product or your simulation result, whatever you're studying. Sometimes just that knowledge of how it's impacting it can provide a lot of insight on your problem and lead you down an interesting path of how you come up and change product designs and so on and so forth. So RAMDO capabilities and features. This is about the most technical. I'm going to dive into this. If you have questions, we can gladly answer them or take them offline. Sampling-based reliability analysis and the RBDO, the reliability-based design optimization. With our sampling method, what's unique about that is the sensitivity is not required. And when I say the sensitivity is not required, we're talking about the sensitivity of your responses. So the sensitivity of your output from your simulation result. Some simulation tools, it is possible to get that information, some it's not. Regardless, it's not required for us for the sampling-based method. Another capability is the uncertainty quantification. And this is just a method of looking at the uncertainty and seeing how it impacts your end result and how you actually apply it or use that information in the end. And I'll show some use case examples and describe those to you in a bit. So some key features within RAMDO itself. We can handle correlated and independent random variables both. We have distribution modeling for both independent and correlated random variables. We have our dynamic Kriging method. That is a unique surrogate modeling method in the sense of what we do with a given set of simulation runs, the DOE. We build, essentially we're building 21 different surrogates, and out of the 21, RAMDO automatically selects which one best fits your given data for you. So dynamic Kriging using it itself is kind of like using one surrogate modeling method, but it's actually using a best combination, looking at the best combinations there are and picking the best one for you to use. And it is very unique in that regard. And then we have this unique local window method, which helps improve results to make them highly accurate, reduces the computational time. Again, the computational time reduction is focused on minimizing the number of simulation runs you actually need coming from that. So I've referred to the simulation runs. RAMDO is simulation-based, meaning we're building on top of a simulation solver to incorporate the uncertainty and variability. RAMDO can be connected with any solver out there is for any discipline. So whether you're doing FEA or CFD or multi-body dynamics or the electromagnetics or casting simulations or whatever simulation you're doing, RAMDO can be connected to it. It could even be an in-house solver you have that maybe you've developed over the years within the company to do very detailed simulations. It could be connected to any of them. So this little bubble diagram here kind of shows a very basic concept of what RAMDO is really doing. You're inputting some kind of variability, the variability of your parameters. This could be materials or loads or manufacturing process or geometry variability, whatever the case may be. You have some kind of simulation model. You're simulating something that you're trying to predict some kind of end result. And combining those two together and feeding those in with RAMDO and will give you the output variability of your simulation. And that is the key thing right there, is the output variability, because that can be used to assess your reliability. It can be used to improve reliability. It can be used to just understand your problem and how it's affecting the end results. So here's one case, one example we did. This was actually a UQ application of RAMDO. And the variability they were looking at here was elevation and soil type. The simulation they were actually doing was, it's called terra mechanics. What it is it's simulating this ground vehicle running over this terrain and predicting how fast, what kind of speed they think they can make going over that terrain. And so the variability they wanted to look at and needed to look at was the variability in the soil and the variability in the elevation. And what they were actually generating as an end output were maps. They call them speed maps. And these speed maps show you, give you the predicted speed range they think will be obtainable over this given scenario. By applying this uncertainty quantification together with this variability in these simulations in RAMDO, we were able to generate a confidence number, essentially a probability number associated with these speed maps. So what we were able to say then is, okay, there's 90% probability you will get the speed shown in the map that's marked as the 90% probable map here. Or there's 30% probability you'll get the speed shown here. That was the type of thing we were able to generate out of it. And so this just provides greater likelihood of mission success in this particular application and a lot of valuable information to them. A second uncertainty quantification example here actually had to do with the human population. So the simulation being done was a crash simulation of a vehicle, and they were analyzing injury risk of the vehicle occupants. The variability that they were trying to handle and address is the variability in the human population, everything from the age, stature, BMI, and gender. And what they wanted to be able to identify, and what we were able to help them do, is identify the different segments within the entire population that were more at risk for injury, and what that segment looked like. So for example, maybe it identifies that short, middle-aged males with a high BMI are at greater injury risk than someone else. And so what it allowed them to do is build a more adaptive restraint systems with different settings for the different population segments and identifying those, which allowed them to reduce the overall injury risk of the vehicle occupants for the entire population. And the last one I'm going to show here is a durability application. And what this one involved was the variability in the geometry and the material properties. The simulation was a durability simulation predicting the fatigue life. And the output then we ultimately got, this was a reliability-based design optimization problem. So the output we got was a new design this A-arm part that you see here with an improved reliability, with the reliability at 98%, reduced the weight by almost 20%, and improved the product life by about 10 times according to the simulation-based method. And so this is what RAMDO was able to do in connection of the variability here with the dimensions and the material properties and the simulation. So this is what we'd call a reliability-based design type of problem and handling that. And so this comes into the optimization part with the uncertainty. So now I'm going to switch gears and I'm actually going to go into a live demo of RAMDO. The demo is going to be a very simple example. We're just going to use a simple plate example here, a finite element model. It's fixed along the edges here, as you can see. We got 2 loads applied to the other edges. And our constraint in this particular case is just the displacement of this corner node highlighted in red. You can see here T1, T2, T3 represent 3 variables in this case. And the variables are just the thicknesses of the plate. So the plate has varying thickness over it. And you can see here we got the material properties, but we didn't change those for this particular application. So I'm going to hop over. So this is the plate model within HyperStudy itself. So you can see here we have a given, see if we can zoom in a little bit. We have the loads applied here. We got the boundary conditions there. And we have all of that going on there. So this is just like you would normally create within your normal FEA, create your model, create your HyperStudy model, create your finite element model. Once we have the finite element model, the way we're connecting this to RAMDO is actually through, or excuse me, this is a HyperMesh model, is actually creating this through HyperStudy. So now here we come to HyperStudy, we've loaded in this plate file, it's connected with the OptiStruct simulation. We're defining the design variables here. You see the T1, T2, T3. They defined the variability with the normal distribution as you see here. And you give the responses here, the mass and displacement. So displacement is that corner node. The objective function is the mass. We want to minimize the mass of this plate. And what we're doing to connect with RAMDO is we're creating a DOE analysis here going on, DOE approach. We have the variables here. We have the 2 responses here. And for the specifications, we're just using a run matrix. So it's a custom run matrix because RAMDO is providing the run matrix to HyperStudy, which is then running the OptiStruct simulation. And so once we have that set up within HyperStudy, you can actually come over to RAMDO. This is the RAMDO user interface here as you see as it first starts up. And I'm just going to select to do the uncertainty quantification for this plate. So I'd make that selection there. And you can see here, if you want to do optimization, that's a choice. We have the sampling based RBDO under there. And we have the surrogate modeling for the dynamic kriging available there. For this example and demonstration, I'm going to do the uncertainty quantification. And I'm going to select HyperStudy as our solver. I'm going to select to import the HyperStudy model. So we'll browse to where that is saved at. And we're just selecting this XML file for the plate, the HyperStudy model, and opening it. And as we go to the next page, you can see here, RAMDO already filled in a lot of this information for us. From the XML file, from the HyperStudy model, we got T1, T2, T3 here, the normal distributions, and then their parameters, the mean and the standard deviation. The HyperStudy variable name over here, this is the name as it was defined within HyperStudy, so this gives you a reference back to the variable it's referring to within the HyperStudy model. If you had any correlation between parameters, you could easily add that in here by selecting, say, T1, and if T3 were correlated, you can select a Coppola type, and you could put in some kind of correlation coefficient there. In this particular case, we're saying the variables are independent, so we don't actually have any correlation. And similarly, we have what we call random parameters that you could use as well. And going on, we have our 2 responses, the mass and the displacement. So we want to say the mass being less than, let's say 2, and the displacement being less than the 0.02, which would be the 2 millimeters. And now we're going to generate these output distribution cases, as we call them here. When I check the variable here, T1, T2, and T3, what we're saying is all 3 variables will be treated as random according to the distribution defined over here. And we're going to generate then the distribution for the mass and the displacement so that we can see what the variability really looks like. Now in the second case, I'm just going to select T1 and T2. So T1 and T2 will be random, T3 will be fixed at its mean value, and we'll generate the corresponding distribution. Then for the third case, we'll just select T2 as being random, and T1 and T3 will be fixed at the mean value. These are just some basic settings. We'll keep the default values. On the review and execute page, we can review what we've input one last time. And we're ready to save the model. I'll just call this webinar. Save it on the desktop here and hit save. And once we've saved it, now we're ready to execute. You can note down here it printed out a message saying that HyperStudy version 14 will be used. So we know which version we're using. We'll hit execute and it will start executing here. And it takes a second for the initial parallel processing part to start and pop up. I'm going to actually pull up so you can see it here. If we would have ran this through a command window, you would see OptiStruct running in the background as the runs come up. But I'm going to show you in the task manager so you can kind of watch for it to pop up here. So you can see here, okay, HyperStudy started. We called HyperStudy in batch mode, and it's running the HyperStudy model. And if you watch here, you'll see OptiStruct pop up over here as it's running the OptiStruct simulations. So RAMDO launches HyperStudy in batch mode, which in turn runs the OptiStruct simulations. There's OptiStruct there that popped up, and there it is again, here popping up. Well, it's going through and it's running the simulations in that manner. And this will continue for all the simulations requested. So you can see here, starting out at requested 11 simulation runs. And so this process is fully automated when you're able to do it this way. There are ways of running things. I'm not going to go into detail here about it, but some of you may be using a cluster to run jobs on or an HPC system. There are ways of using that in connection with this, and if you have those kind of questions, we can gladly address those probably offline because those can be kind of involved depending on your particular system you're using. And you can see here RAMDO is going through. It asked for another set of runs up here, asked for 5 more, then it finished. Now it's constructing the dynamic kriging model here. Printing out some results here, we're seeing what the reliability was of this given design here. For the mass one, it's about 75%. For the displacement one, it's about 48%. Now what it's doing is it's actually creating the histogram results, the distributions. And so now that it finished, you can see it actually took us over to the results section. And you can see here, okay, it generated the distribution of the mass when variables T1, T2, and T3 are random. And it generated it for when for the displacement as well, when all 3 variables are random. And then here we have the mass when just variables T1 and T2 are random. And similarly, the displacement when variables T1 and T2 are random. T3 at this point in time is just fixed by its mean value. And then here's the mass when only variable T2 is random. And here's the displacement when only variable T2 is random. And this type of thing, this problem is pretty simple and it's a very straightforward problem. So you don't see a significant change between things. But you can see in this particular case how the distribution did narrow a little bit. It's between 1.9 and 1.95, whereas when all variables are random, it goes all the way over to the 1.9. On the right-hand side, it didn't really change too much. Here it's just above the 2.1. Here it's just under the 2.1. But if you're doing a more complex problem, this type of information can be valuable because these changes between when all variables are random versus one variable is random could be quite drastic, and it can help identify which variables in your problem are really critical when considering the uncertainty and the variability. And then the table results we have here show you the mean value, the nominal value, and your standard deviation of your responses and the reliability that we asked it to calculate that we saw before. In this particular case, because this problem is simple, straightforward, and essentially a linear problem, nominal value and mean value are one and the same. If your problem's nonlinear, these values will not be the same, they will be different. So that's where this kind of information can come into play, and it can also help you gain a deeper understanding of what's going on with your particular problem. So the next example, and I'm not going to do a live demonstration of it due to the time constraint, but now if you wanted to take this plate example here, and we see, okay, the reliability of the mass is 75%, that we might not care about so much, but the reliability of the displacement was only 48%, meaning there's only 48% probability that this plate would actually survive under the given loading conditions and usage we have modeled. And so the question is, well, how can I improve that? I don't want half my plates to fail that I'm producing, so how can I improve that? And that's where doing RBDO itself, reliability-based design optimization, would come into play. So if you could actually set up the RBDO and import the plate model, I believe I have a copy of that already completed. So I'm just going to open up that model to show you. So here we set up the optimization, sampling base, reliability based design optimization from the current design. Similar as we did before, we're using HyperStudy as a simulation solver. These options here are grayed out and these ones here are grayed out because we already ran this model, so they're disabled, meaning the model was already ran. Similarly, the same information was brought in. The only additional information here, because we're doing optimization, is we needed to know what the design space was, the design bounds. So we can see that here with the lower bound and the upper bounds. The same performance measures as before. Now the new information that comes in is now we're defining, okay, the mass performance measure is going to be our objective function. That's what we want to minimize. The second one is going to be the displacement. The second one, the displacement, is going to be our constraint. So we're constraining that. We are saying the displacement should be less than this 2 millimeters, and we want to have a target reliability at 95%. So we want to take it from this currently 48% reliability, and we want to get it to 95% reliable. We're just using the basic settings, optimization tolerances, your typical review, and then we actually ran this and actually got some results. So it's got a number of results. I'm going to go through these a little bit. First one I want to show here, and I'm going to close that one. I'll drag this down here. I'm going to show this history plot. So the light blue here is the mass and the dark blue is the displacement. Keep in mind that the mass is the objective function that's plotted on the left axis here. In the displacement, what we're actually plotting is the reliability of the displacement, because keep in mind, we wanted to take that from the 48% and get it up to 95%. And so down here on this x-axis, this is the optimization iteration history. And you can see if you follow the displacement along, we started here, which is this right axis, and it's at the 48%. And during optimization, you can see how the reliability improved and finally leveled off to converging, and we're at that 95% reliability that we specified. At the same time, you can see the mass here started out down here, and in order to improve the reliability, the mass had to be increased. And that's pretty typical for most all RBDO problems. If you're starting at a design that's not as reliable as you want, most likely your cost function or your objective is going to have to increase in order to achieve that target reliability. Basically, there's no free lunch. You have to pay a little bit in order to get that reliability that you want. And you can see down here on this displacement, the initial reliability is 48, the final one was the 95, and you can see we are output like the initial mean values and nominal values for this problem, being it's kind of a linear problem, these are essentially about the same, so there's no big difference between the nominals and the means. But if it was nonlinear, like I mentioned before, you would see a significant difference potentially. The key point of what you're getting out of this, it's we increased the reliability 95%, so how do we actually go about doing that? Well, what RAMDO actually gave you is, these are your design variables here, the 3 we had. So this middle column gives you your initial thickness values here, as you can see, and the right column gives you the RPDO value. And you can see there for T2 and T3, the 2 variables are essentially identical. They didn't change. The one that did change was T1. You had to increase it from the 0.096 to the 0.1 in order to improve the reliability. So that's ultimately what RAMDO gave you out of doing the reliability for that problem. So I'm going to jump back to the presentation now. So I just highlighted that in RAMDO, but we went from this initial reliability of 48%, we took that to the 95%, and in order to do that, what we had to do is we had to change this T1 variable and increase it by 1 centimeter thickness, and that increased our reliability from the 48% to the 95%. So that concludes the demonstration of RAMDO and what you can potentially all do with it. It can be used for the uncertainty quantification if you just want to see what your variability is, or it can be used in the design process, taking variability into consideration to improve your reliability and tell you how you need to change your design in order to improve the reliability. So here's our contact information, myself, Kurt, and KK on there as well. If you have any questions, detailed questions, or want more information, or want another demo or a deeper demo, or questions on how to apply it to your problem, feel free to reach out to us at any time. Thank you.
All right, thank you, Nicholas, for the presentation. We will open the QA lines now. If anybody does have any questions, please feel free to type those. But we do have a few quick poll questions for everybody. And that is our first question, do you currently do optimization? All right, thank you, everyone. We'll go ahead and get started. Nick, our first question is, how do you estimate reliability based on the response surface and address the inherent inaccuracy in the RSM?
All right, that's a great question. I'm going to back up to this slide here. Is my screen still showing?
Yep, it's still showing.
Perfect. Okay, so yes, when dealing with using an RSM or response surface or surrogate model, meta model, whatever you want to call it, there's always a question of accuracy. So the unique thing about RAMDO is 2 things. Our unique thing especially is this, what we call it, local window. What it is we're only creating the surrogate model, the response surface, in this local window area. So think of it as this, and that local window area is defined by this input variability here. So if we look at this, just look at the red outer circle, if that represents kind of your area of variability, we're only creating the surrogate model within this area, which means we can focus the DOE within that area because we're only evaluating the reliability, the variability in this area. We don't care about the rest of the design space. It doesn't matter to us at this point in time. We'll put this variability in there. We create the DOE in here, which makes our surrogate model very accurate in that regard. The other thing that we have is the dynamic kriging itself, which is it automatically chooses the best surrogate model of 21 possible kriging models. So there's 21 possible kriging models for this given local window, and we're automatically choosing the best one that fits the DOE that you have for this area. And then for optimization, once optimization tells you to move to this point, we're constructing a new local window. If there are simulation runs that previously were ran that fall within this window, we'll reuse those. Otherwise, we're using new simulation runs over here, and it's an iterative process. And what we found is that you can actually build a very accurate surrogate model this way, and yet you tend to reduce the number of DOE required compared to if you tried to build a surrogate model over the entire design space and to the accuracy you would get here, and then carry out the reliability design optimization on that surrogate model.
All right, our next question. What simulation tools can RAMDO be used with?
So that kind of comes back to here. essentially, it could be used with anything, whether you're doing FEA, CFD, multi-body dynamics, the electromagnetic, any of the Altair ones. If you got a third-party one or an in-house one, any of those could be used. If you're going, especially with the Altair stuff, you can easily go through HyperStudy connection like we did with OptiStruct to connect to the solver that way. You can write your own code to do that. We can help you set up and write code to do that. I've connected to a lot of different solvers out there and a lot of different disciplines before.
All right. We do have a follow-up from the first question, and they would like to know how scalable it is and how many random variables can you handle?
The random variables that we can handle, the most we've tried it on to date so far has been 20. Because once you go beyond that, as you're probably well aware, the accuracy of the surrogate model becomes a even bigger question mark. We do have a unique feature of a filtering process to reduce variables down that we've successfully used. So if you want more information on that, please contact me and I can help you with that part of it. And then what was the first part of the question? How scalable?
Yes, yep.
I guess I'm not 100% certain what they mean by how scalable it is. If they're talking about the number of variables or the number of responses, we can have any number of responses. And we've used this in connection, kind of going to the second question, multidisciplinary applications where we've had like CFD and FEA in one problem setup. But if they can elaborate a little more on the scalability, I might be able to answer that better.
Okay, they're saying scalability as in number of variables. Yeah.
Okay. So yeah, I think I kind of hit that already. We've used it on up to 20 so far and have found we've gotten really accurate results when we kind of did a brute force comparison. Going beyond that, I've played with some things there, and I'll talk to anybody offline who wants to talk more about that, but I think that's probably deep enough for this conversation.
Okay, great. Our next question, how do we incorporate the CAE analysis result reliability?
How do we incorporate, what was that again? The CAE result?
The CAE analysis result reliability.
Okay, I'm not 100% certain if I fully understand what they mean by that, but I'm going to jump back to this here actually. So the CAE result is, it's used, the main way we're using the CAE result is building a surrogate model. And once we have this surrogate model built, then we're actually calculating the reliability of the given design. But you can see here, in this particular case, the displacement, at the nominal value would be the value of the response at the current design. If you just ran your CAE simulation and got the value, you get this value. The mean value, as you can see here, which is a little bit different in this particular case, you would have here is, that's the mean given the randomness. So those could be different, and so that's kind of related to your CAE simulation though. I'm not 100% certain I answered their exact question in that regard, so if they can give more detail on what they really mean or what they're really looking for, I could probably give a better answer.
Okay. It looks like they did just follow up. Analysis has a lot of assumptions involved, including the modeling variation from person to person. The results can be different.
Yes, absolutely. And that's a great question. And that could come in a lot of different ways. One way of looking at that, if you want to kind of compare models and the variability and how it's affecting things, might be doing a UQ thing where you use one simulation model and you generate this distribution. You use the other simulation model and you generate the distribution, and you can see how well the two compare. And then if you have experimental data to compare it against, you can see if the experimental data falls within the realms of these distributions and where they fall at in there. If they're scattered pretty evenly throughout, you've probably covered it. If the experimental data is all on one end or one side or the other, maybe that leads to questions on the accuracy of the simulation model. Our method is built on the simulation model. So essentially we're kind of making an assumption here. Our method is accurate in terms of the simulation model. So it's going to be as accurate as your simulation model. But yes, simulation models always have assumptions and inaccuracies within them as well.
Okay, a follow-up from the same audience member. Assuming that the FEA result for reliability is 90%, how can we incorporate this 90% into the final result?
I guess if the FEA result is 90% reliable, how can we incorporate this into the final result?
Yeah.
Not 100% certain I know what they mean by that. I guess, well, I'll go back to, let me pull this back up here. I guess it kind of like this plate example, in this case is 95% reliable. And the final result we got from doing this, if this is what they're referring to, is it gives you the final design that you have. So if you want your product to be 95% reliable or 90 or whatever your target is here, it would give you this final design. It's telling you how you need to change your design in order to achieve that reliability. Not sure if that's exactly what they were meaning or if they might have more.
Okay, we can wait for their follow-up, or we can also contact you after the webinar. So I'll move on to the next question. Where do I get the variability and uncertainty information for my parameters to enter into RAMDO?
That's a great question. It really depends if you know what kind of variability you're looking at trying to handle or address. If it, for example, if it's manufacturing variability, you could probably go over to the manufacturers and talk to them and ask them questions about the variability in their process and their tolerances and that kind of thing. If it's, say for example, if it's sheet metal, like maybe in this plate example that we did, if you're getting a piece of sheet metal from a supplier that you're using to produce something, that supplier probably can give you some kind of variability on the thicknesses and their tolerances, and probably some kind of confidence associated with it too. Experimental measurements or data, sometimes that's possible depending on what the variables are. It can be done in a laboratory where you can go out, you can actually take actual measurements, get some realistic data points, and then that's where our distribution modeling can be used to come up with the information that you need to actually plug into RAMDO. If you're really uncertain about the variability or what it really means, I would suggest reaching out to us and talking to us. We've worked with people before where they're like, well, yeah, we're pretty sure we have variability, but we don't know where to start or where it goes. And usually after I sit down and talk to them, I can start asking questions and we can quickly identify the variability.